Hi, my name is Schuyler. I'm one of the Chisel and FIRRTL developers. And today, I'll be talking about, initially with something that makes me very sad. So a lot of times people will say to me, and any presentation should start with a straw man argument, but people will come to me and say, oh, Schuyler, the Chisel seems cool, but the Verilog is unreadable spaghetti code. And that makes me very sad because I really don't think that that's a fundamental limitation, but it's just a feature request or hopefully a pull request away from being better. And there's been a lot of work over the past, I'd say about 3 months that has gotten the Verilog generation qualities way up. So 2 big takeaways from this. So the first is that just an overview of a lot of these efforts to improve Verilog emission, which initially were things that I was doing, but then a lot of other people stepped up, and I'll try and highlight some of that work with this talk. And then finally, of some ideas of where you can actually get involved with relatively small changes to the code base, which have dramatic quality of life improvements for users and verification teams. Okay, so with this, I'm going to be walking through a small example of Chisel code, and really all of this is just a multiplexer, which has 4 cases here. So you have an input, you have a select, and you have an output. And I'm using a Chisel 3 utility called mux lookup. And all of this is doing is saying if it's 0, the output's going to be a bit select of in. If it's 1, it's a bit select with some other type conversions, or simple operations like binary or negation. And this is simple, right? If you wrote this up in Verilog, you'd expect to get something like this, right? Nicely ordered, you get a nice always at pos edge clock, and you have a case statement, and the assignment is there. This is what you would expect to get, right? This looks about the same as this. So however, you go take this, and you run this through the Chisel and the Chisel compiler and the FIRRTL compiler, and you get this. This is the actual Verilog output. Okay, not quite the actual Verilog output, but it's not that much better, right? And sort of just high level, what's wrong with this? One is there are, I guess we have up through temporary underscore T underscore 15. There's tons and tons of temporaries. There's all of this massive if-def chunk, which seems to get copied around all the time. And then you have this beautiful structure here that is if begin, end, else begin, if begin, end, else begin, if. So on, right? This is way far away from what you would expect to get. So the sort of non-answer here is, well, the QOR is the same, or the QOR is good, so it doesn't really matter. And this is true, right? If you take this big mux tree and you feed this into Verilator or VCS, you're going to get executables that run at good speeds. If you feed it into your FPGA toolchain, Vivado doesn't care. Intel tools don't care. Cadence or Synopsys, they eat this stuff up, right? Yes, Martin? Okay. Sure. So that I do admit, so that yes, you can potentially get the quality of the FPGA tools improved if you actually use the correct statements. So with that, however, even though the QOR is the same, it's not the same for everybody, right? And readability really does matter, okay? So the design team says the quality of results is the same, and the verification team wants to kill you. Well, yes, exactly. This is an actual HR incident that happened. So anyway, but the thing is, the whole point of this talk is that, the Verilog that you get out of this, we can make it better, and it's just that for the very same reason that the quality of return is the same, is just there's a lot of low-hanging fruit that just hasn't been optimized. And a lot of these things are very small changes, and I'm just going to try and highlight a couple of them that really get these massive improvements out of it. Okay, so there's sort of 3 types of improvements that I'm going to go over. One is the Chisel generators should be better. Things in the Chisel standard library should and can be better. The Verilog emitter itself can also be better. And then finally, there are new FIRRTL compiler transforms, which can actually get the FIRRTL in a better shape for the Verilog emitter to spit it out. All right, so first thing, improving the Chisel generators. So if you take a look at this code here, so on the left, this was the Chisel that I showed originally. So this is that mux with this mapping. And this is what I get out on the right. And the immediate thing that you will look at this and notice as the problem is the left, there are 4 cases, and I have a 2-bit select line. So it's completely full. But over here, I have 5 cases. And you look at this, and this was actually I believe a real question that came from Anton Blanchard, who's going to talk after me, when he was using mux lookup. And he was saying, why are there 5 cases? So the reason for that is that mux lookup has a default parameter that is sort of the fall-through case. And that case here, true, is always going to be emitted by Chisel. But the simple thing here is, why not just go through this, and if the mux lookup is full, don't emit the default case? Okay? Pretty simple. You could go and take through this and try and do some satisfiability analysis, but why not? I mean, just look at this and see if it's full and be done. So this diff is shown for the PR that actually fixed this. This was Chisel 3 PR number 1201. And I realize this is not really intended to be readable, but look at the size of this thing. This is about 10, 15 lines added, and it's not really that much. Now, and I do have to also say that I don't think he's here, but Albert Magyar, a Berkeley PhD student, did help out with this and got all of the corner cases for this change correct, which I had originally missed in the initial PR. But fundamentally, all that's going on here is that you're building up a set of a map of all of the different keys that you're using for the map. And then if that mapping is full, don't emit the default. Otherwise, emit the default. And just make sure you handle all of the edge cases here. So an edge case in this case is that you have a 2-bit line. If you give the key is 4, that's going to alias to 0. Just make sure that you're handling you're doing the keys correctly in terms of the widths. And the fundamental thing, though, here is this diff is tiny. And this is something which is able to actually make a big impact on the output Verilog that you're getting. So I'm going to go over a couple more of these changes here, and then I'm going to get back to what the actual output Verilog code looks like. So stay tuned for that. So the second thing here is improvements to the Verilog emitter. And so first off, I have to kind of take a step back and just give my spiel of what the process of going from Chisel down to Verilog looks like. So I usually view this as a sort of 3-layered, 3 stages, if you will, of Chisel runs, that generates FIRRTL IR, the FIRRTL compiler runs, that generates more FIRRTL IR, and then the Verilog emitter runs, and that takes FIRRTL IR and goes to Verilog. Now, however, it's not quite that simple. So if you kind of take this Verilog emitter and then blow it up, there's actually inside of the Verilog emitter a sequence of transforms. Some of these are grayed out because they're new and they were not originally used with the code that I showed. But there's stuff in here that you may have heard of. Things like dead code elimination does actually run inside of this. But for the most part, it's not really too much of a concern of what's going on here. But way down here at the bottom, there's an actual emitter step. And this is the thing that's taking some FIRRTL with modifications that have been made here and doing the actual conversion to Verilog. All right, so now if we take one step back and look at the code again, so this is that if-else block that we saw here before. But the problem here is, well, why are we only emitting if and else, and why aren't we emitting else if, right? That would flatten this whole thing down and make everything look a lot better. So the reason for that, fundamentally, is that the FIRRTL IR has no notion of like an else when. It's only when and else. And that's great because it makes the thing super simple to analyze and just simplifies the complexity of any kind of transform that you have to write. But it has some problems for this emission. Because what really is going on here is this is just a naive emission of the FIRRTL IR. And what it turns out is the modification else if is, almost is that just whenever you look at a mux, if the false condition is another mux, that's an else if. That's basically all that it is. So this is code inside of the Verilog emitter that was added in pull request 1204. And really the only thing that's going on here is one line down here. There was some refactoring of this to make it a little bit cleaner, but, and it's nice that I can actually go up here and kind of poke this. But what you're looking at is for each mux, you're looking at the true value and the false value. And based on the true value and the false value, you do something, right? So there's 5 cases here. Number 4 was added. I'm just going to enumerate them quickly. First, if the true value and the false value are both self-assignments, just don't emit it. There's nothing going on. If the true value is a self-assignment, you take the condition of the mux, invert it, and just use the false condition in its place. If the, actually, I got that backwards. If not, no, I did get that right. Third, if the false condition is a self-assignment, just skip it. Just emit the true condition. And then finally down here, if the false condition is a mux, then you emit the true condition, and then you do some magic here to emit it as an else if. Okay, I realize this is like, there's a lot of pattern matching here and a lot of Scala, but fundamentally what this is that this is one case that I'm adding, and that's really all that it is. Okay, so now sort of taking one step back, and again, I'm leaving the big reveal until the end, but then sort of the third level of improvement that you can make here are new FIRRTL compiler transforms. So just jumping back here, revisiting this and talking about these are actual transforms that are added inside of the Verilog emitter. So there's been a big push at Sci5 to sort of inline all of the temporaries that you may have. So things like taking inversions and inlining them, bit extractions and inlining them, and casts and inlining them, and that has then had a dramatic decrease in the number of temporaries. However, I can't take credit for doing this because I didn't do it. But there's been a lot of work by Jack Koenig, who unfortunately couldn't be here, from John Ingalls at Sci5, who is in the room. I've done some stuff, but it's not finished yet. And then also a recent pull request that came in from Derek Pappas from Sci5. So I think the slides are going to be available. So if you want to dig into more detail on some of the actual internals that are going on here, you can. But you can kind of just take my word for it that all of this is improving the quality of the output Verilog. All right, so where are we now? So the first thing is less temporaries. So this is the code that was for that Chisel. If you run this through Chisel 3.2.0, which corresponds to FIRRTL 1.2.0, you get this, up through T15. If you run it through now, this is what you get. So it's basically, in terms of ignoring the I/O, this is about half the size. Okay? This is, remarkably better if you give this to a verification team. They're going to be a lot happier with this as opposed to something like that. All right? So in terms of else if emissions, so this is where we started at with Chisel 3.2. You have 5 cases, and it's all of this else, this if else, and with the modifications that we have on master, this is what you get now. So the key thing is that now you get this nice else if emission, and also things which I did not do, but you have the inlining of some of these temporaries. So in this case, you're taking this not in bit extract, and that's all just put in one statement. So this looks a lot better. If you give this to a verification team, at least they can get that, this is describing something that kind of looks like a mux, as opposed to something which, looks like a computer wrote it. So putting this all together, this is what that full example looks like in the FIRRTL all on one slide. And as you can see, these boxes have decreased a lot in size. I haven't done anything specifically talking about this big if-def randomization logic. It's not clear that we can do something with that, but there may be strategies of just trying to get this down so that it's either in a header file or something like that so that it's not polluting the code. All right, so big idea here. Better Verilog emission is just a feature request, or better yet, a pull request away. So the real thing here is that what I've tried to show with some of these examples, and I realized that there was a lot of code that was flying by, but just that with relatively small changes, you can make a big impact on the resulting Verilog that you get. And it's one of those ways where if you want to be a Chisel or a FIRRTL developer, which I'll talk about some more tomorrow, there are a number of outstanding things that you could think about on how to try and then make the Verilog emitter better for everybody and for your verification teams. So one thing which I've been playing with, which is not complete, is if you start from this if-else-if logic, it's not that hard to then think about emitting case statements. So there's a branch I've been playing with on trying to get case statement emission working, and that even better describes the intent of the designer. There's a lot of stuff currently where if-def blocks aren't grouped together, and that would be a relatively straightforward change for somebody to tackle. Additionally, this else-if generation that I'm showing is only applicable for register updates. So the reason for that is the combinational logic is emitted, muxes in this case are emitted using ternary statements, and those you can't sort of group nicely. So I've been thinking about if it makes sense, and if it's something that you think would be useful for your projects, of using always at star or other things to then try and allow for better structure of combinational logic in addition to register updates. So one thing that some of you may not know is that we actually do technically have a system Verilog emitter, which I guess in this case the -x means system Verilog compiler, which currently is just the Verilog compiler, but it gives you a .sv suffix. So, and if Verilog is a subset of system Verilog, then it is system Verilog, guys. But there's a lot of stuff that we could think about adding into this. So some of this is more just semantic differences of always com, always flip-flop, those types of things. But the real win here is potentially on the ability to use structs. So this is something where then the bundles that you describe in Chisel are then actually available and have better semantic meaning in the resulting system Verilog in this case. And then if you're looking for something that is probably more of a big challenge issue, is that currently we have common subexpression elimination in the Verilog and system Verilog compilers. But that does leave some stuff on the table, and you may be able to think about adding in a global value numbering transform, which will do sort of different things. So that's all that I had, and I think I'm under time, so I may have time for one question or something like that.
Thanks. Any questions, Schuyler?
I'm just curious. Earlier we heard that the great thing about Chisel is you emitted some universally acceptable form of Verilog. And if people are jumping in and emitting new versions of Verilog, is there any validation or independent checks?
Yeah, so so the question was that before we've heard stuff about emitting a common set of Verilog that all the tools can read, and I'm talking about potentially emitting things which are different from that. So I do think we have to sort of figure out what the common denominator is here across tools. I don't know exactly what that would be. I mean, things like else-ifs are, sort of obvious. Those would be supported. But I think we'll then have to, do some due diligence to figure out what things are supported, because if we start emitting Verilog that is not usable by tools, then that's problematic. And I do also realize that with something like system Verilog emission, we do also need to make sure that it is equivalent to the Verilog, and that is a hard problem. And I'm, aware of it, but I'm not sure what we can do.
So similarly, I think niceness to read is one thing, but correctness is always first and foremost for the verif guy. How do you prove all these transforms and emission paths are correct?
So that is also a hard problem. Currently we don't have any specific proofs for that. We can kind of ignore that issue for now because all the verification is done on the Verilog, right? But there have been some efforts or some people thinking about it, I think, Edward Wang has been thinking about trying to do some formal verification of FIRRTL transforms so that we can prove sort of what they're doing and reason about them. But at this point, that's all sort of open work. Did you want to jump in, Adam?
You guys are going to have Anton back to 10 minutes.
Sorry. Oh yeah, and just as a follow-up, if as you're doing these improvements, you don't necessarily need to prove. You just need to prove that what you emitted was the same as what you emitted without the new transform.
Correct.
So you can actually do LEC to ensure that the two generated Verilogs of the two different versions are the same for your design. And we have set up continuous integration where we run Yosis on the generated Verilog for each PR on a set of regressions to try and catch these.
Thanks, Adam.
All right, thanks.
Okay.
So let's transition now over to